Imagine standing on a mountaintop at twilight, watching the sun sink toward the horizon as shadows lengthen and the first stars appear. The day is ending, but slowly, gracefully, with a beauty that comes from knowing that this particular arrangement of light and shadow will never happen exactly the same way again. Now imagine that same twilight stretched across not hours, but billions of years, and you begin to understand what we might be witnessing in the cosmos around us. What if the universe itself is in its evening hours, and we're among the last observers of its fading glory? Tonight, we're going to journey through cosmic time to discover that the universe may have already experienced its noon, its moment of maximum brightness and creativity, and is now settling into a long, slow evening that will last trillions of years. We'll explore the possibility that every star we see, every galaxy we observe, every cosmic phenomenon we study is part of the universe's final sunset, magnificent, but irreversibly fading toward darkness. The story begins in violence. 13.8 billion years ago, the universe exploded into existence from a point smaller than an atom, expanding faster than light itself and creating space, time, matter, and energy in a single moment of unimaginable creativity. But that initial burst of expansion, known as inflation, lasted less than a trillionth of a second. What followed was a more gradual cooling and evolution that continues today. In those first moments after inflation ended, the universe was filled with pure energy, no matter, no atoms, no structure of any kind. The temperature was trillions of degrees, hot enough to prevent even the most basic particles from forming stable bonds. But as space expanded, it cooled, and that cooling allowed the first particles to condense from pure energy like droplets forming from steam. For the first few minutes of cosmic history, the universe was a nuclear reactor, fusing hydrogen into helium in ratios we can still detect today. Then it cooled below the temperature needed for fusion, and for the next 380,000 years, it remained a hot, opaque fog of hydrogen and helium gas, glowing like the surface of a star, but gradually dimming as expansion carried that heat across ever larger volumes of space. Then came the cosmic dawn. The universe cooled enough for electrons to combine with protons, creating the first neutral atoms. Suddenly, light could travel freely through space for the first time. The cosmic fog lifted, and the universe became transparent, releasing the radiation we now detect as the cosmic microwave background, the afterglow of creation itself. But dawn was followed not by daylight, but by darkness. The universe entered what cosmologists call the Dark Ages, a period lasting nearly 200 million years when no stars shone, no galaxies existed, and space was filled with nothing but cooling gas and invisible dark matter. It was during this cosmic night that gravity began its slow work, pulling matter together into the first structures that would eventually become the seeds of everything we see today. Dr. Maria Gonzalez stands before a wall of monitors in the control room of the Atacama Large Millimeter Array, studying radio signals from the edge of the observable universe. What she sees challenges everything scientists thought they knew about how quickly the cosmos organized itself after the Big Bang. The data shows massive, mature galaxies existing when the universe was barely 400 million years old, galactic metropolises that formed impossibly fast in what should have been the universe's rural youth. It's as if we discovered a fully developed city in what we thought was pristine wilderness, she explains to her research team. These early galaxies are too organized, too massive, too chemically evolved for their age. The universe hit the ground running in ways we never expected. What Gonzalez and her colleagues are witnessing is evidence of the universe's first golden age, a period of explosive creativity that began when the first stars ignited and ended when the cosmic environment became too sparse and evolved to sustain such rapid growth. This golden age lasted roughly 3 billion years, from cosmic dawn until the universe was about 4 billion years old. During this period, star formation rates were 10 to 20 times higher than anything we observe today. Galaxies collided and merged with incredible frequency, triggering massive bursts of stellar birth. Supermassive black holes grew from stellar mass seeds to billion solar mass giants in just a few 100 million years, powering quasars so bright they could be seen across the entire observable universe. The first stars were unlike anything that exists today. Made almost entirely of hydrogen and helium, the only elements available in the early universe. These population III giants were monsters, hundreds of times more massive than our sun. They burned blue-white hot, converting matter to energy at rates that made them visible across cosmic distances, but their fuel supplies lasted only a few million years. When these primordial giants died, they didn't fade quietly. They exploded as parent-stability supernovae, more powerful than any stellar explosion observed in the modern universe. These explosions were so energetic they could destroy entire star-forming regions, but they also scattered the first heavy elements across space: carbon, oxygen, silicon, iron, all the building blocks of rocky planets and ultimately of life itself. Dr. James Liu, a theoretical astrophysicist at Princeton, has spent years modeling these ancient explosions and their effects on early cosmic evolution. His computer simulations reveal a universe far more violent and creative than the relatively quiet cosmos we inhabit today. The early universe was like a cosmic construction site where everything was happening at once, Liu explains during a lecture to graduate students. Massive stars were being born and dying in rapid succession. Black holes were growing exponentially. Galaxies were crashing into each other constantly. It was creative chaos on a scale we can barely imagine. But this cosmic construction boom couldn't last forever. As the universe expanded, the dense gas clouds that fueled rapid star formation became increasingly dispersed. The frequency of galactic mergers decreased as space grew larger and galaxies moved farther apart. The raw materials that had powered the first stellar generations were either consumed or locked up in long-lived stars and stellar remnants. Gradually, the universe entered what we might call its mature phase, the cosmic afternoon when star formation settled into steadier, more sustainable patterns. This is the universe we know today, where stellar birth occurs at predictable rates in well-organized galaxies, where supermassive black holes have mostly stopped growing, where the violent creativity of youth has given way to the more measured evolution of middle age. But even this mature phase shows signs of decline. The Hubble Space Telescope's surveys of galactic evolution reveal that star formation peaked when the universe was just 2 to 3 billion years old and has been declining ever since. We're already living in the universe's afternoon, and the shadows are beginning to lengthen. The evidence is everywhere once you know how to look for it. The most distant quasars, those brilliant beacons powered by rapidly growing black holes, are all ancient. Their light has been traveling toward us for over 10 billion years. No quasars exist in the present-day universe because the dense gas needed to feed black holes at such extreme rates was consumed long ago. Dr. Rachel Kim, an observational cosmologist at the Harvard-Smithsonian Center for Astrophysics, discovered this pattern while creating a census of quasar activity across cosmic time. Her research revealed a sharp peak in quasar brightness when the universe was young, followed by an equally sharp decline that continues today. "We missed the show," Kim told colleagues at a major astronomy conference. By the time our solar system formed, the universe had already lived through its most energetic period. The quasar era, when supermassive black holes were growing rapidly and shining across cosmic distances, was already ancient history. The numbers are staggering. At the peak of quasar activity, these objects were consuming matter at rates of hundreds of solar masses per year, converting a significant fraction of that matter directly into energy through the process of accretion onto spinning black holes. The most luminous quasars were producing energy equivalent to 1 trillion suns, visible across billions of light-years of space. Today, the supermassive black holes that once powered quasars still exist at the centers of galaxies, but they've gone dormant. Occasionally, one might flicker briefly to life when an unlucky star wanders too close or a gas cloud falls inward. But these events produce only pale echoes of the ancient brilliance that once filled the early universe with light. The death of the quasar era represents more than just the end of one cosmic phenomenon. It marks the universe's transition from youth to maturity, from rapid growth to gradual decline. The dense, gas-rich environment that made quasars possible also enabled the explosive star formation rates that characterized the universe's golden age. As that environment evolved and dispersed, both phenomena faded together. Dr. Elena Vasquez, studying this transition through observations with the Very Large Telescope in Chile, describes it as cosmic aging in real time. We can see the universe getting older by looking at galaxies at different distances, she explains. The most distant ones, seen as they were billions of years ago, are blue and vibrant with young stars. Closer galaxies, representing more recent epochs, are increasingly red and mature, dominated by older stellar populations. This cosmic archaeology reveals a universe that has consumed most of its star-forming fuel. The hydrogen and helium that powered the first stellar generations have been processed through successive generations of stars, either locked up in long-lived stellar remnants or dispersed so widely by stellar winds and supernovae that they can no longer collapse to form new stars. The universe is running out of the raw materials needed to maintain its current level of stellar activity. Computer models predict that star formation will continue to decline for billions of years, eventually dropping to levels so low that the night sky will be dominated by the slowly cooling remnants of earlier stellar generations. Professor Michael Chen, a galactic evolution specialist at UC Berkeley, has created what he calls the Cosmic Star Formation History, a comprehensive timeline showing how the universe's stellar productivity has changed over its 13.8 billion-year lifetime. The graph reveals a clear pattern: rapid rise during the first few billion years, a peak around 3 billion years after the Big Bang, and steady decline ever since. We've already made about 95% of all the stars the universe will ever create, Chen explains to a gathering of science journalists. We're living through the final 5%, and that remaining stellar birth is happening at an ever-decreasing rate. The universe's stellar factories are shutting down. This revelation transforms our understanding of humanity's place in cosmic history. We're not witnessing the universe in its prime, but in its decline. The spectacular stellar nurseries visible in modern telescopes regions like the Eagle Nebula and the Carina Nebula are becoming increasingly rare. Future epochs will see such star-forming regions only as historical curiosities, relics of an age when the cosmos still possessed the energy and raw materials for large-scale stellar creation. The transition is already visible in the types of stars being born. The massive, short-lived giants that dominated early stellar populations are becoming extinct as the universe's metallicity increases and its gas becomes more dispersed. Future generations of stars will be smaller, redder, and longer-lived stellar pensioners that will burn their nuclear fuel slowly and steadily for trillions of years. Dr. Lisa Park, who studies stellar evolution at the Space Telescope Science Institute, has modeled this transition in detail. Her work shows that we're witnessing the end of the universe's age of stellar giants. Those brilliant blue stars that light up galaxies and die as spectacular supernovae after just a few million years of existence. The universe is transitioning from spectacular but brief stellar fireworks to modest but long-lasting stellar candles, Park explains during a symposium on cosmic evolution. It's becoming more conservative with its energy, more focused on longevity than brilliance. The cosmic sunset is beginning. This stellar transition has profound implications beyond astronomy. The massive stars that are going extinct are also the primary factories for elements heavier than iron, gold, platinum, uranium, and other heavy elements that are created only in the extreme conditions of stellar cores or supernova explosions. As these stellar giants disappear, the universe's capacity for creating chemical complexity will diminish dramatically. The periodic table itself tells the story of cosmic decline. Elements up to iron can be created in the cores of ordinary stars through nuclear fusion. But elements heavier than iron require more extreme conditions, either the incredible pressures found in the most massive stars just before they explode, or the violent collisions of neutron stars that create brief, localized conditions even more extreme than stellar cores. The recent detection of gravitational waves from neutron star mergers has provided direct evidence of this heavy element creation. When the LIGO and Virgo detectors observed the collision designated G170,817, Follow-up observations revealed the explosion synthesizing vast quantities of gold, platinum, and other precious metals. More than the mass of several Earths' worth of heavy elements created in a single event lasting just a few seconds. But such neutron star mergers depend on the prior existence of massive stars that lived and died as supernovae, leaving behind neutron star remnants that could eventually spiral together and merge. As massive stars become extinct, the raw material for creating neutron stars disappears, and these spectacular mergers will become increasingly rare. Dr. Anna Mueller, a gravitational wave astronomer with the LIGO scientific collaboration, studies the rates of these cosmic collisions across different epochs. Her analysis reveals that we're living through the peak era for neutron star mergers, the brief period when the products of early massive star death are colliding at maximum rates. In a few billion years, neutron star mergers will become extremely rare events, Mueller explains during a conference on gravitational wave astronomy. We're witnessing the universe's final attempts at creating the heaviest elements. The cosmic periodic table is essentially complete. This completion of the periodic table represents another milestone in the universe's transition from creativity to conservation. Future planets will be formed from the stellar debris of earlier epochs, but they will receive no significant additions of heavy elements from ongoing stellar nucleosynthesis. The chemical diversity that makes complex worlds like Earth possible is becoming a fixed resource rather than a renewable one. The implications extend to the possibility of life itself. Complex chemistry, including the carbon-based chemistry that underlies terrestrial biology, requires a diverse palette of elements created through stellar nucleosynthesis. If the universe's capacity for creating new elements is declining, then the conditions favorable for life might also be becoming increasingly rare. Dr. Emma Watson, an astrobiologist studying the chemical requirements for life, has investigated how stellar evolution affects biological possibilities across cosmic time. Her models suggest that the galactic habitable zone, the region around each galaxy where conditions are favorable for life, has been shrinking as stellar evolution progresses. Early in cosmic history, there weren't enough heavy elements for rocky planets to form, Watson explains to a conference of planetary scientists. Now we're entering a period where heavy elements are abundant but becoming fixed in quantity. In the far future, stellar evolution might make the universe less friendly to complex chemistry and biological processes. This perspective transforms the search for extraterrestrial life from a quest for communication to a search for fellow participants in the universe's brief biological experiment. If life requires specific conditions that are becoming rarer over cosmic time, then any civilizations we discover will be contemporaries of our own epoch, witnesses to the same cosmic sunset we're observing. The search for extraterrestrial intelligence takes on new urgency in this context. SETI researcher Dr. Carlos Rodriguez has reframed his work around the idea that we might be living during the universe's final era of widespread biological activity. If complex life requires the products of massive star nucleosynthesis, and if massive stars are becoming extinct, then we might be among the last civilizations the universe will ever produce, Rodriguez explains during a SETI Institute lecture. Contact wouldn't just mean meeting aliens. It would mean meeting fellow witnesses to cosmic biology during its final flowering. This biological perspective on cosmic evolution suggests that consciousness itself might be one of the universe's final achievements. The emergence of intelligence capable of understanding cosmic history occurs just as that history becomes most visible and most threatened by future changes. We are, perhaps, the universe developing the capacity to witness its own sunset. But even as stellar evolution progresses towards smaller, longer-lived stars, and even as the raw materials for planetary formation become fixed in quantity, the universe continues to evolve in ways that create new forms of beauty and complexity. The cosmic web of dark matter filaments that connects galaxy clusters across billions of light years is itself a structure of incredible elegance, revealed only recently through computer simulations and observational surveys. Dr. Hassan al-Rashid, mapping large-scale cosmic structure through radio telescope observations, describes the cosmic web as the universe's most magnificent architecture. His surveys trace dark matter filaments stretching across hundreds of millions of light years, connecting galaxy clusters in a network that resembles neural pathways in a vast cosmic brain. We're seeing the universe's skeleton, Al-Rashid explains during a presentation on cosmic structure. These filaments of dark matter provide the scaffolding along which ordinary matter flows to build galaxies and stars. It's architecture on a scale that dwarfs anything we see in individual galaxies. But this cosmic architecture is not permanent. The same dark energy that ended the quasar era and slowed star formation is now beginning to affect the cosmic web itself. As space expands at an accelerating rate, the filaments connecting galaxy clusters are stretching and weakening. Computer simulations predict that the cosmic web will gradually dissolve over the next 100 billion years, leaving each galaxy cluster isolated in an ever-expanding void. The discovery of dark energy in 1998 revealed that the universe's expansion is accelerating rather than slowing down as astronomers had expected. This acceleration is driven by a mysterious component that makes up about 70% of the universe's total energy content, but interacts only through gravity, causing space itself to expand at an increasing rate. Dr. Amanda Foster, a theoretical cosmologist studying dark energy's effects on cosmic evolution, describes it as the ultimate expression of cosmic aging. Dark energy represents the universe's transition from a gravity-dominated phase, where matter clumped together to form increasingly complex structures, to an expansion-dominated phase where everything is pulled apart. Her calculations show that dark energy's dominance will only grow stronger over time. As the universe expands, matter and radiation become increasingly diluted, but dark energy maintains constant density. What began as a minor component of cosmic energy is destined to become completely dominant, eventually overcoming even the strong nuclear force that holds atomic nuclei together. We're witnessing the universe's final phase transition, Foster explains to a gathering of cosmologists. Gravity built up cosmic structure for the first 10 billion years of cosmic history. Now dark energy is tearing it down, and that process will continue until even atoms themselves are ripped apart. This far-future scenario, known as the Big Rip, represents the ultimate cosmic sunset, not just the end of star formation and galactic evolution, but the destruction of matter itself. However, current observations suggest that dark energy's strength remains constant rather than increasing exponentially, which would delay such catastrophic effects for many trillions of years. Even without a big rip, dark energy's continued dominance ensures that the universe will become increasingly cold, dark, and isolated. Galaxy clusters will be carried beyond each other's gravitational influence. Individual galaxies will exhaust their star-forming gas. The final generations of stars will burn out, leaving only slowly cooling stellar remnants scattered through an ever-expanding void. Dr. Robert Chen, running cosmological simulations of the universe's far future, has visualized this cosmic evening in exquisite detail. His models show galaxy clusters separating until they can no longer interact, individual galaxies consuming their remaining gas in final bursts of star formation, and stellar populations evolving toward long-lived red dwarfs that will burn steadily for trillions of years. The far future will be dominated by stellar conservation rather than stellar creation, Chen explains while demonstrating his simulations. The universe will become incredibly efficient at extracting energy from its remaining fuel, but that fuel will be strictly limited. It's like transitioning from a bonfire to carefully rationed candles. These red dwarf stars, too small and cool to be seen with the naked eye from significant distances, will dominate the universe's far future. They can burn their hydrogen fuel for up to 10 trillion years, nearly 1,000 times longer than the universe's current age. But even they will eventually exhaust their nuclear fuel and fade to darkness. The final stellar remnants, white dwarf stars, neutron stars, and black holes, will represent the universe's last organized structures. White dwarfs will cool slowly toward absolute zero over timescales measured in trillions of years. Neutron stars will spin down and cool, becoming invisible lumps of degenerate matter. Black holes will persist longest of all, slowly evaporating through Hawking radiation over periods so vast they challenge comprehension. Dr. Lisa Worden, studying these extreme timescales through theoretical physics, has calculated the lifespans of various cosmic structures in the far future. Her work reveals a universe that will persist for incredible lengths of time, but in increasingly simple and isolated forms. A solar mass black hole will take 1067 years to evaporate completely through Hawking radiation, Worden explains during a lecture on extreme astrophysics. The supermassive black holes at galactic centers will persist for 100 years or more. The universe will be dominated by these slowly evaporating remnants long after every star has died. Yet even within this narrative of cosmic decline, there are possibilities for continued complexity and perhaps consciousness. Some physicists speculate that sufficiently advanced civilizations might learn to extract energy from the rotation of black holes, or to create new forms of order even in an expanding, cooling universe. Dr. Miguel Santos, investigating the thermodynamics of intelligence in the far future, believes that consciousness might find ways to persist far longer than the stars. His calculations suggest that information processing becomes increasingly efficient as the universe cools, potentially allowing complex computations to continue even in the final stages of cosmic evolution. Intelligence might be the universe's way of creating memory and meaning that can outlast physical structures, Santos proposes during a symposium on consciousness and cosmology. Through understanding and information processing, conscious beings might preserve cosmic memory long after the last stars have died. This possibility transforms the cosmic sunset from ending to transformation. If consciousness can find ways to persist and evolve in the far future, then the universe's transition from physical complexity to informational complexity might represent not death, but metamorphosis, a cosmic creature entering a new phase of existence. But these remain speculative possibilities. What we can observe and measure today is a universe that has already lived through its golden age of stellar creation and is now settling into a long, slow evening. The cosmic sunset is not a future event. It's happening around us right now, visible in the declining rates of star formation, the dormancy of once-active quasars, and the gradual stretching of the cosmic web itself. Dr. Jennifer Liu, principal investigator for the James Webb Space Telescope, sees this sunset in every image her instrument captures. The telescope's infrared vision can penetrate the dust clouds that often obscure stellar nurseries, revealing star formation in galaxies so distant that their light has been traveling toward us for over 13 billion years. Every deep-field image shows us the universe during its youth, when star formation was vigorous and chaotic, Liu explains during a press conference releasing new Webb observations. But we also see the beginning of the decline, early galaxies starting to exhaust their gas, the first signs of the cosmic aging process that continues today. The emotional impact of these observations extends beyond scientific measurement. Each image represents a moment in cosmic history that will never be repeated, a glimpse of phenomena that no longer exist anywhere in the present universe. The galaxies Webb observes in the deep past are fossil light from a cosmic ecosystem that has gone extinct. Dr. Sarah Kim, analyzing Webb's observations of the earliest galaxies, describes the experience as cosmic archaeology. We're studying the remains of the universe's youth, preserved in ancient light that has been traveling toward us since before our galaxy was even fully formed. It's like discovering a lost civilization, except the civilization is the early universe itself. This archaeological perspective reveals how much of cosmic history we're already missing. The very first stars, those massive population III giants that ended the cosmic dark ages, lived and died before any current galaxies had formed. We can only infer their existence from the heavy elements they scattered through space and the effects they had on subsequent stellar generations. The first quasars, those brilliant beacons that lit up the early universe, existed in a cosmic environment so different from today that they might as well be from another universe entirely. The dense gas clouds that fed them have long since been dispersed or consumed. The rapid galactic mergers that triggered their activity have become increasingly rare as cosmic expansion carries galaxies apart. Even the cosmic microwave background, that faint afterglow of the Big Bang that fills all of space, is gradually fading away. This radiation has been cooling and redshifting for nearly 14 billion years, growing fainter with each passing moment. In the far future, it will become so diluted that no instrument will be able to detect it. The universe's birth cry will fade to silence. Dr. Elena Martinez, studying the cosmic microwave background with ground-based and space-based instruments, sees this fading as a cosmic memory loss. The CMB contains information about the universe when it was only 380,000 years old, the oldest light we can observe, she explains. But that light is getting fainter and more redshifted every year. Future civilizations might have no direct evidence that the Big Bang ever occurred. This gradual erasure of cosmic history by the expansion of space itself adds urgency to current astronomical observations. We're living during perhaps the only epoch when the universe's full story can still be read in the electromagnetic radiation reaching us from across space and time. The responsibility this creates extends beyond individual scientists to entire civilizations. If we are among the final witnesses to cosmic phenomena that are fading from observability, then our observations and records take on significance beyond mere scientific curiosity. We're creating a permanent archive of cosmic history for whatever intelligences might follow us. This archive exists in multiple forms. Scientific databases preserve our measurements and observations. Computer simulations model cosmic evolution across vast timescales. Artistic works capture the emotional and aesthetic dimensions of cosmic discovery. Together, they represent humanity's contribution to cosmic memory, our attempt to preserve understanding of the universe during its most observable epoch. Dr. Neil Sharma, director of the upcoming Extremely Large Telescope project, views his mission as creating humanity's final comprehensive survey of the observable universe. The ELTS 40-meter mirror will collect more light than any previous ground-based telescope, pushing the limits of what can be observed from Earth's surface. We're building this telescope not just for current research, but for cosmic memory, Sharma explains during a project review. This might be our last opportunity to observe the universe at its current level of complexity and accessibility. Dark energy is already beginning to hide parts of cosmic history from us. The ELT will search for the spectroscopic signatures of the very first stars, study the atmospheric compositions of potentially habitable exoplanets, and trace the evolution of galaxies across cosmic time. Each observation will add to the comprehensive record of cosmic evolution that we're creating during this brief window of maximum observability. But even as we document cosmic decline, the universe continues to surprise us with unexpected forms of beauty and complexity. The detection of gravitational waves has revealed a cosmos that remains capable of spectacular violence, even in its mature phase. Black hole mergers release more energy in gravitational waves than all the stars in the observable universe emit in light, creating ripples in spacetime that carry information about cosmic evolution across billions of years. Dr. Anna Kowalski, analyzing gravitational wave data from the LIGO Virgo KAGRA network, sees these detections as messages from the deep past. Every gravitational wave we detect carries information about stellar evolution, galaxy formation, and cosmic structure from earlier epochs, she explains. We're receiving time capsules from the universe's more active periods. The pattern in gravitational wave detections reveals cosmic aging in real time. The black holes merging today formed from massive stars that lived and died when the universe was younger, and star formation was more active. As stellar evolution progresses and massive stars become extinct, the raw material for creating new black holes will disappear, and gravitational wave detections will become increasingly rare. We're witnessing the final phases of a process that began with the first stellar deaths over 13 billion years ago, Kowalski notes. Each merger represents the end result of stellar evolution during the universe's more creative epochs. When these mergers stop occurring, we'll know that the universe has truly entered its final phase. The upcoming LISA Space-Based Gravitational Wave Observatory will extend these observations across the entire history of the universe, detecting mergers from the earliest epochs of stellar death to the final black hole coalescences billions of years in the future. This cosmic ear will listen to the universe's evolution across its full lifespan, documenting the transition from rapid stellar creation to gradual stellar death. Yet gravitational waves also reveal that the universe's creative capacity hasn't entirely disappeared. The merger of two neutron stars observed in 2017 created quantities of gold, platinum, and other heavy elements worth more than Earth's entire economy. These rare collisions continue to enrich the universe with the raw materials for complex chemistry, even as the massive stars that create neutron stars become extinct. The ongoing search for exoplanets has revealed another dimension of cosmic creativity that persists despite stellar decline. The Kepler Space Telescope and its successors have discovered thousands of worlds orbiting other stars, from rocky planets like Earth to exotic super-Earths and mini-Neptunes that have no counterparts in our solar system. Dr. Rachel Torres, studying exoplanet demographics across galactic populations, has found that planetary systems continue to form even as star formation slows. The galaxy is still making planets, she reports during an exoplanet conference. Star formation may be declining, but stellar systems are still assembling the building blocks for complex worlds. The diversity of exoplanets suggests that the universe's capacity for creating potentially habitable worlds hasn't disappeared, even if it's operating at reduced rates compared to the past. Rocky planets forming today benefit from billions of years of stellar nucleosynthesis, incorporating heavy elements that weren't available to the first planetary systems. This raises profound questions about life's prospects in a universe that's past its creative peak. If biological complexity requires specific chemical and physical conditions, and if those conditions are becoming rarer over cosmic time, then life itself might be part of the cosmic sunset we're witnessing. Dr. Emma Watson's astrobiological research suggests that we might be living during the universe's brief, biological window, the period when stellar evolution has created sufficient chemical complexity for life, but hasn't yet progressed to the point where suitable stellar environments become rare. Complex life requires a delicate balance, Watson explains to a gathering of astrobiologists. Stars must be stable enough to maintain habitable conditions for billions of years, but massive enough to have synthesized heavy elements in previous generations. That balance exists now, but it might not persist as stellar evolution continues. The implications transform the search for extraterrestrial intelligence from a quest for communication into a search for fellow participants in the universe's final biological experiment. Any civilizations capable of interstellar communication would be our contemporaries in cosmic time, sharing the experience of consciousness emerging during the universe's twilight years. Contact with such civilizations would represent more than first contact. It would be a meeting of cosmic sunset watchers, each bringing their own perspective on what it means to be conscious during the universe's transition from creativity to conservation. The scientific and philosophical exchange could provide insights into consciousness's role in cosmic evolution and its prospects for surviving into the far future. SETI researcher Dr. Elena Rodriguez has reoriented her search strategies around this cosmic context. Rather than broadcasting generic mathematical messages, her team now focuses on signals that demonstrate understanding of stellar evolution, galactic dynamics, and the universe's long-term trajectory. Any civilization advanced enough for interstellar communication would understand that they're living during a unique period in cosmic history, Rodriguez explains. They'd want to share their observations of cosmic decline, to compare notes on what it means to be conscious during the universe's evening. The possibility of such contact takes on new urgency given the cosmic timescales involved. If consciousness is indeed rare and tied to specific phases of cosmic evolution, then current civilizations might represent the universe's only opportunity to achieve self-understanding through intelligent observation. The telescopes we build, the equations we derive, The simulations we run all represent the cosmos developing the capacity to study its own aging process. Through science and observation, matter organized as conscious beings traces the story of its own cosmic origins and contemplates its eventual fate. Dr. Carl Hendricks, a veteran astronomer preparing for retirement after 5 decades of cosmic observation, sees this self-understanding as perhaps the universe's greatest achievement. We are the universe becoming aware of its own mortality, he tells his final graduate seminar. Through our observations and theories, the cosmos is learning to contemplate its own sunset. This cosmic self-awareness emerges just as the universe becomes most comprehensible and most threatened by future changes. The cosmic microwave background provides clear evidence of the Big Bang, but it's gradually fading beyond detectability. Distant galaxies reveal cosmic evolution in action, but dark energy is carrying them beyond observational reach. Even gravitational waves from ancient stellar deaths will eventually cease as the universe runs out of massive stars to create black holes. The timing seems almost providential intelligence developing the tools to understand cosmic history, just as that history becomes most visible and most endangered. Whether this timing represents coincidence or some deeper principle remains one of the great mysteries of cosmic evolution. What's certain is that we exist at a unique moment in cosmic time, when the universe can still be observed and understood across nearly its full lifespan. The phenomena we study today, stellar nucleosynthesis, galactic evolution, cosmic expansion, represent the universe displaying its full complexity for perhaps the last time in cosmic history. Future civilizations, if they exist, will inhabit a cosmos with less visible structure, fewer observable phenomena, a smaller and lonelier observable universe. They might find traces of our observations preserved in some form in data archives, in artistic works, in the physical modifications our activities have made to our cosmic environment. Through these traces, they could learn about the universe's more complex and connected phase, when evidence of cosmic evolution stretched back nearly to the Big Bang itself. Our current observations might serve as their only window into the cosmic history that will no longer be directly observable. This transforms every astronomical measurement from scientific curiosity into historical preservation. Every star catalog we create, every galaxy survey we complete, every cosmic phenomenon we document becomes part of a permanent record of the universe during its sunset years. The record we're creating extends beyond pure science. Artists inspired by astronomical discovery are creating works that capture the emotional dimensions of cosmic evolution. Composers translate the mathematics of stellar oscillations into musical harmonies. Poets find language for the ineffable vastness of cosmic time and space. Together, these scientific and artistic responses represent humanity's attempt to create meaning from cosmic impermanence. We're not just documenting the universe's decline, we're finding beauty in its temporary nature, significance in its fleeting complexity. Dr. Maria Santos, a philosopher of science studying the existential implications of cosmic evolution, sees this meaning-making as itself a form of cosmic creativity. Through art and science, through poetry and mathematics, consciousness is adding new forms of complexity to the universe even as its physical complexity begins to decline. This suggests that the cosmic sunset might not be entirely about loss and decline. Even as stellar formation slows and galaxies drift apart, consciousness creates new forms of order and beauty through understanding, creativity, and the preservation of memory. The universe's transition from physical complexity to informational complexity might represent not ending, but transformation, matter achieving the capacity to understand and preserve its own history, even as that history fades from direct observation. Standing beneath the night sky, astronomers around the world continue their patient vigil, collecting ancient light and decoding its messages about cosmic evolution. Each photon that reaches our telescopes has traveled across vast distances and cosmic time, carrying information about stellar births and deaths, about galactic collisions and cosmic expansion, about the universe's long journey from simplicity to complexity and back toward simplicity again. But that ancient light also carries something more evidence that the universe has achieved something remarkable during its brief moment of maximum complexity. In creating stars and galaxies, planets, and ultimately consciousness, the cosmos has built structures capable of understanding their own origins and contemplating their own fate. We are the universe's final gift to itself, the capacity for self-awareness emerging just as understanding becomes both most possible and most necessary. Through our observations and insights, the cosmos is learning to appreciate its own beauty even as that beauty begins to fade. The sunset we are witnessing is not just about ending, but about recognition. For the first time in cosmic history, the universe has developed the capacity to see itself clearly, to understand its own evolution, to appreciate the magnificent structures it has created over nearly 14 billion years of expansion and cooling. Dr. Amanda Foster, working late in her Cambridge office, studies computer models that project cosmic evolution far into the future. Her calculations show dark energy gradually overcoming all other forces, carrying galaxies beyond each other's gravitational reach, stretching the cosmic web until it snaps, leaving each surviving structure in perfect isolation. In 100 billion years, observers in any remaining galaxy will see a universe that appears to contain only their local group of stars. Foster explains to a late-night video conference with colleagues around the world. The cosmic microwave background will have cooled and redshifted beyond detection. There will be no evidence that other galaxies ever existed, no proof that the universe had a beginning, no way to reconstruct the cosmic history that we can observe today. This future isolation creates a profound temporal asymmetry. We can see the entire history of cosmic evolution stretching back to the Big Bang, but future observers will have access to an increasingly limited view of cosmic structure and history. The universe is not just aging, it's forgetting its own past. The gradual erasure of cosmic memory by expansion and redshift means that current observations might represent the only permanent record of the universe's full evolutionary history. The data flowing into observatories around the world carries information that will never again be directly observable from any location in the cosmos. This realization has transformed the motivation behind major astronomical projects. The extremely large telescope, the Nancy Grace Roman Space Telescope, the proposed next-generation space observatories, all represent humanity's attempt to create a comprehensive archive of cosmic phenomena before they fade beyond observational reach. Dr. Jennifer Liu, analyzing the latest images from the James Webb Space Telescope, sees each observation as both scientific measurement and historical preservation. The telescope's infrared vision reveals star formation in galaxies so distant that their light began its journey when the universe was less than 5% of its current age. We're documenting the universe during its youth, when stellar formation was explosive and chaotic. Liu explains while reviewing images of galaxies from over 13 billion years ago. But that youth is preserved only in ancient light. The physical structures that created these images evolved long ago into something completely different or ceased to exist entirely. The temporal displacement inherent in astronomical observation creates a unique form of cosmic archaeology. Unlike terrestrial archaeology, which studies physical remnants of the past, astronomy observe. Our witnessing is not just about ending, but about recognition. For the first time in cosmic history, the universe has developed the capacity to see itself clearly, to understand its own evolution, to appreciate the magnificent structures it has created over nearly 14 billion years of expansion and cooling. Dr. Amanda Foster, working late in her Cambridge office, studies computer models that project cosmic evolution far into the future. Her calculations show dark energy gradually overcoming all other forces, carrying galaxies beyond each other's gravitational reach, stretching the cosmic web until it snaps, leaving each surviving structure in perfect isolation. In 100 billion years, observers in any remaining galaxy will see a universe that appears to contain only their local group of stars. Foster explains to a late-night video conference with colleagues around the world. The cosmic microwave background will have cooled and redshifted beyond detection. There will be no evidence that other galaxies ever existed, No proof that the universe had a beginning, no way to reconstruct the cosmic history that we can observe today. This future isolation creates a profound temporal asymmetry. We can see the entire history of cosmic evolution stretching back to the Big Bang. But future observers will have access to an increasingly limited view of cosmic structure and history. The universe is not just aging, it's forgetting its own past. The gradual erasure of cosmic memory by expansion and redshift means that current observations might represent the only permanent record of the universe's full evolutionary history. Every star catalog we create, every galaxy survey we complete, every cosmic phenomenon we document becomes part of preserving the universe's memory of itself during its most observable epoch. Dr. Carl Hendricks, in his final semester before retirement, often takes his students outside on clear nights to observe the Milky Way. After 5 decades of cosmic observation, he's developed a profound appreciation for the fleeting nature of cosmic beauty. Every time we look up at the night sky, we're seeing the universe's sunset in slow motion, he tells them. The stars seem eternal, but they're burning fuel that becomes more precious as the cosmos ages. The stellar nurseries, where new stars are born, are becoming rarer with each passing eon. Even the galaxies themselves are being pulled apart by dark energy. Yet Hendricks doesn't find this knowledge depressing. Instead, he sees it as a reminder of how precious and meaningful this cosmic moment truly is. The fact that consciousness emerged just as the universe became comprehensible, just as its full history became observable, strikes him as almost miraculous. We are the universe's way of watching its own sunset, he reflects, gesturing toward the Milky Way stretching overhead. Through our eyes and instruments, the cosmos is learning to appreciate its own beauty even as that beauty begins its long fade toward darkness. The cosmic sunset we're witnessing isn't an ending, it's a transformation. The universe is transitioning from an era of physical creativity to one of conscious understanding. As stellar formation slows and galactic structures stretch apart, intelligence and awareness emerge to preserve the memory of what the cosmos achieved during its golden age. In observatories around the world, astronomers continue their patient work of cosmic archaeology, collecting ancient light that carries messages from the universe's youth. Each photon that reaches our telescopes completes a journey across space and time, connecting us to stellar births and deaths that occurred when the cosmos was young and creatively abundant. We exist at the perfect moment to serve as cosmic witnesses, late enough for intelligence to evolve, but early enough to observe the full sweep of cosmic history. In studying the universe's sunset, we're not just documenting decline, but participating in its greatest achievement, the emergence of consciousness capable of understanding and appreciating the magnificent story of cosmic evolution. The sunset is beautiful precisely because we're here to see it, to understand it, to preserve its memory in the vast library of human knowledge and experience. Through science and art, through observation and imagination, we ensure that the universe's story continues even as its physical structures slowly fade into the expanding darkness of space and time.